Hello and welcome to Monday's edition of Cracking the Cryptic, where today we've got a debut on the channel for the constructor barrels, and a puzzle called Cloaked in Night Winds. Now, I did not know what this referred to. I typed it into Google and it referred me to some death metal music. Now, I'm not into death metal. Many of you out there will be able to tell me whether Cloaked in Night Winds is a standard of any sort. I don't know. What it's got to do with Sudoku, I have no clue. What it's got to do with this Sudoku, even less clue. But we shall, I'll read you the rules of this one in a moment, and we shall all learn together. Apparently this is a brilliant puzzle, of course. What you wouldn't expect, anything less. I've got a couple of bits of news for you today, actually. We got mentioned on Yogscast yesterday by Lewis. Look. In their video. It was amazing. They're an enormous YouTube channel. They've got something like 7 million subscribers, and they watch little old us. Fantastic to hear that. Although I have to say that Lewis's comments about what I might be doing after I finished the puzzle were completely untrue. The less said about that, the better, I think. The other thing, of course, that we've got coming up for you, if you're a patron of the channel, oops, that's not in the right place. If you're a patron of the channel over on Patreon, we have our Christmas gift in the offing. This is a quite extraordinary puzzle stroke Sudoku hunt from Peter Venus, Aspartagus and Panthera. And when I say quite extraordinary, I mean quite extraordinary. I do not know how many hours I spent on this and Mark spent on this over the last 2 weeks. It is a great many, and finishing it was one of the great triumphs, frankly, in my puzzle solving life. It is just magnificent, and we're probably this weekend is when we're going to release it to everybody who's supported us on Patreon. Thank you so much if you're one of those people. This Christmas gift, I think, well, you'll like it. That's all I should probably say. Now, what else do I want to mention? I want to mention, actually, occasionally over on Twitter, I do tweet cryptic crossword clues, and I tweeted this one from the constructor Dean Mayer, which appeared in the Sunday Times. Bringing up a child causes, and the enumeration is 7,8. I won't tell you the answer now. I might tell you the answer if I remember at the end of the video. And someone suggested this might be a good thing for YouTube Shorts, which I think are like 1-minute videos that you can do on YouTube. I am quite tempted by that, actually. So maybe Cracking the Cryptic will venture into YouTube Shorts in the near future. I don't know where we're going to get the time to do this. I really don't. But it does sound like quite a cool idea, and it appeals to me. Anyway, all that said and done, let's get on with Cloaked in Night Winds, and I'll read you the rules. We have got normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage. So, for example, those 3 cells have to contain digits summing to 13. Now, this was the tricky bit of the rules. I read the rule set earlier, and this is really where it gets very unusual. Cells containing circles are the upper left cell in a region of size x by x, where x is the digit in the circle. Digits can repeat within a region, and the digits in each region must sum to the same total, but the digits in the circles can be different. So this seems to be saying, if we put a 5 in here, for example, and this actually might be a bad example because it might be a clue to what's going on in the puzzle. Although actually, no, it's not, because this can't work. Okay, this is good. We'll go through this version of the example. So if this was a 5, it would be defining it would be the upper left cell in a region, in a 5 by 5 region. So it would be defining this blue square. Now let's imagine this can't be a 4, but let's imagine it was a 4. That would be saying that this region here would be a 4 by 4 region, and then we're told that we can repeat digits within orange, we can repeat digits within the blue region, but the sum of the digits in the blue would have to equal the sum of the digits in orange, which is really weird. It's a very unusual constraint, and in fact impossible, due to a theorem discovered by Aard van der Wetering based on set theory. So this is definitely not the right configuration, and we can see that anyway because there are 4s pointing at this 4. But we're going to have to work and work out what's going on. It sounds very interesting. Let me get rid of... Oh, let me just restart the puzzle. That's going to be the quickest way of doing this, rather than me ineptly clicking around the grid. Do have a go. The way to play is to click the link under the video as usual. Now I get to play, reposition my glasses. Let's get cracking. Now, I presume... I'm just scanning these cages that we've got to see if I can see anything interesting, and I don't think I can. So I suppose we've got to think about the possible sizes of the squares that are going to emanate from these two clues. Now the problem is there are a lot of ways of doing this. For example, this... Sorry, I pressed the wrong button there. That would in theory work, wouldn't it? That would be a square of size 1, where they certainly sum to the same thing. So this needs to be disproved somehow, because otherwise this is certainly a possible orientation. Ah, right, yeah, okay. I can see why this doesn't work. This doesn't work because you can't make this a 1 because of the 9 cage. Because if this is a 1, this 9 cage has to be 2, 3, 4. It's the only way of making 3 cells add up to 9 without repeated digits if you can't use a 1. And look, 4's here and here, kibosh that very efficiently. So, these are not 1s. Now, what about 2s then? Can we make... I suppose if this is a 2, these 4 squares now add up to 11, using the power of maths. Now those 3... Ah, yeah, okay. Those 4 squares cannot add up to 11, because we've already got 8 in one of them, so the other 3 cells would all have to be 1s, and that's going to break the rules of Sudoku. So that means... And this can't be... Yeah, this can't be greater. That's the other thing I've got to think about, actually, is whether you can mismatch these clues and have one of them being one number and the other one being another. So that doesn't work, though, does it? You can't make this bigger because you can't make it 2, and any bigger is going to break it by even more. So this is not 2 in the top left corner. So it's at least 3. Now, being at least 3 is already very interesting because, of course, of the secret. Now, the secret is, and I only tell this to people who are in my very close affection, the secret is that any complete box of a Sudoku, or any complete row, or any complete column, sums to 45 if you add all its digits together, because, by the rules of Sudoku, these 9 cells are the digits 1 to 9. These 9 cells are the digits 1 to 9. These 9 cells are the digits 1 to 9. If you add up the digits 1 to 9, you get 45. So we know now that this one is adding up to at least 45. But we don't know... Oh. Well, hang on. That cannot... Oh. Sorry, I'm saying oh a lot because I think I've realised something very obvious. I'm just checking it in my mind. We know that because this adds up to at least 45, it's definitely not a 2 by 2. I'm saying that. No, that can't be a 2 by 2, can it? 998. 9988 is only 34. So no, it's not a 2 by 2. So it's at least a 3 by 3, but it can't be a 4 by 4 or a 5 by 5. It can't be a 5 by 5 for obvious reasons. It would go off the end of the grid. So it must be a 3 by 3. Maverick's making an appearance. Maverick's been quite grounded recently, but it appears that he's about to fly past my window. Yeah, so that must be a 3 by 3. Because we know that its cells in its square, in the square that we generate off this cell, must add up to at least 45, and possibly much more if this number is not a 3. Yeah, okay, so let's highlight those then. Now, Is there some way of knowing that this is a 3? It sort of feels like it's going to be, doesn't it? A 4x4 is going, that we have to, where the sum of this has to equal this, feels unlikely to me. What is the absolute minimum I could make a 4x4 add up to? If I do 45 here, those squares, I'll minimize them as 1, 2, 3 and 4, so that's another 10. And I'll do a 1, 2, 3 in there, that's another 6, so it's 16, 61. 61 is the absolute minimum I can make a 4x4 add up to. And the absolute maximum I could make this add up to would be a 9 and 7 in those squares. And then 9, 8, 9, 8, I suppose, with the 8s having to appear in those squares. So 8s and 9s like that. So that would give me 24, 29, 32, and 34 is 66. Oh, 66, that's more than enough. Oh, right, okay. Right, this has been, well, interesting, I suppose. That can be a 4. That can be a 4 because I can make plenty enough here. If I max out these digits, I can make these add up to 66, and these are a minimum of 61. So, that's not good, is it? I don't even know whether or not... So I don't even know what this is. And therefore I don't have a clue what the composition of the gaps in this one are. And that's very annoying. Ah, right, but the 9 cage rescues me again. Good lord, this is I really like this so far. It's really original. That can't be a 3, not because of all this work we've been doing on the sizes of squares emanating from the corners, but because if it's a 3, what's the nature of this 9 cage? Well, by Sudoku it's got to have a 5 in it, and therefore it's got to be 1, 3, 5, but I've just put a 3 in the corner. And that's 3 in the corner, and that 3 in the spotlight losing its religion has really messed it up for the 9 cage. It's impossible to be in the corner. So that's not 3 in the corner. It doesn't work. So that's got to be a 4. And that, well, I say it's got to be a 4. I mean, I'm assuming it can't be a 5. 5 would be ridiculous, wouldn't it? Let's just check that, actually, because I should double check it. We know these max out at 66. No, it can't work. I mean, the minimum I could make those 6 cells would be 21. The triangular number for... Oh, you can't make them 21 anyway, but let's just check. If we did manage to make them 21 and 21, so we're saying each of these six sums is the digits 1, 2, 3, 4, 5, and 6. Put 1, 2, 3, and 4 in those 4 cells. That would be another 10, so that's 42, 52, no, 97. 97 is definitely greater than 66. That cannot be a 5. That is a 4. We should highlight these digits then. And now we've got some Sudoku we can do. 4s have got to be there. 4s have got to be here due to the symmetry. 4 in the 9 cage would cause it to be 2, 3, 4, which would make this a 5, 6 cage, which would have to go this way round, 5 here, 6 here. Oh, and I was just going to say that would force a 5 into the 9 cage, but of course these 5s already do that. Once this isn't a 5, you've got to put 5 in the 9 cage, so that's 1, 3, 5. The 12 cage can't be 4, 8 anymore, so that's 5, 7, or that's 5, 7, or 3, 9, which looks like it's almost interesting, but not quite. So what are we saying? We are saying, or the puzzle instructions are telling us, that these cells sum up to the exact same thing as these cells. And there isn't that much flexibility because we can max this, we can min this out at 61 think it was 61. Was that right? 45 plus 10 plus 16, yeah, 61. And we could max this out at 66. So there are several degrees of freedom, unfortunately. And I sort of want to do some sort of set trick on this, but the only set trick I know definitely doesn't involve those cells. It involves all of those cells with the 4x4 in the corner. Oh, that's it. Ah, that's right. Well, when I say that's it, it may not be it, but it's definitely interesting. That is definitely interesting. Whoa, I like this. This is seriously clever. Okay, it can be shown that the blue cells in this grid are the exact same digits as the green cells, plus a complete set of the digits 1 to 9. Now we know that a complete set of the digits 1 to 9 add up to 45. And I know in this puzzle that the green is the exact same sum as the purple. So if I was to remove all of the green cells, so what I'm saying is, I'm not saying this in a very articulate way. So green equals blue. No, green plus 45 equals blue. But green also sums to the same thing as purple. So if I remove purple from blue, I must get 45. So those cells come out, and I get this ring of cells has to equal 45. I'm not actually sure that's very helpful, to be honest. Let me just, but I'm troubled here. I'm troubled because what I'm not doing is explaining why I know that this green thing here equals this blue thing, or the green thing plus 45 equals the blue thing. So let me explain about green and blue things to everybody, in case you've not seen the Aard van der Wetering trick. And this trick is very straightforward. It's one of the most straightforward applications of set theory. And the way we're going to do that and prove it to ourselves is we are going to highlight the top 4 rows of this grid in green. Now, these 4 green rows, we don't know how the digits are disposed within these green rows. We've got no clue. But we do know that each row individually contains a set of the digits 1 to 9, and therefore we can describe the green cells altogether as 4 sets of the digits 1 to 9. Now I want to imagine that I write each of those digits, each of those 36 digits, on a different Scrabble tile, a different green Scrabble tile, and I put it in a bag. This bag here, a green bag full of 36 Scrabble tiles. Now I'm going to create a different bag of Scrabble tiles. I'm going to create a blue bag of Scrabble tiles. And my blue bag of Scrabble tiles is going to have some more tiles in it. Because what I'm going to do is I'm going to have 5 sets of the digits 1 to 9 in my blue bag of Scrabble tiles, 5 complete columns of the grid, and I'm going to put those 45 Scrabble tiles in a blue bag here. So you can see this bag contains 4 sets of the digits 1 to 9. This bag contains 5 sets of the digits 1 to 9. So the difference between the bags at the moment is 1 set of the digits 1 to 9. Now, if I was to look at this 4, and I was to take a 4 out of this bag and out of this bag, take those 4s out, 1 Scrabble tile from each, and throw them away. What's the difference between my Scrabble tiles now, this bag and this bag? It's still 1 set of the digits 1 to 9, because it was 1 set of the digits 1 to 9 was the difference in the bags before I did anything, and I took the same digit out of both bags, so it still must, the difference between the bags must be the same. So any cell in the puzzle now, or any digit that corresponds to any of these cells that have two colours in them, if I remove their Scrabble tiles from both bags, the conclusion remains the same, that the difference between the blue bag and the green bag is one set of the digits 1 to 9. So that's where we get to using set theory, but in this puzzle there is an additional consideration, because in this puzzle we're told that the sum of the green Scrabble tiles is identical to the sum of those cells, these yellow cells. So that means, given that we know that the difference between green and blue is one set of the digits 1 to 9, and we know one set of the digits the digits 1 to 9 adds up to 45, well, we can cancel this from the blue region, cancel those cells from the green region, and we're just left with the 45 being the difference between the two regions. So this set of digits here must sum to 45, and that is fascinating, but I'm not sure how important it is for solving the puzzle. It does feel, I'm going to make those purple again, although actually no, for colour blindness I should make them orange, sorry, because I know that blue and orange I think are the best differentiated colours for most people who suffer from colour blindness. So I have learnt more stuff about the puzzle. Originally I only knew about the relationship between green and orange. I've now learned that there is a completely separate consideration applying to blue. And that, hang on a sec, 15, 15, 15, 15 and 12 is 42. Yeah, that's quite interesting as well. If we try and minimise the values of the blue region, we know the blue region adds up to 45 in this puzzle. And if we try and just keep absolute minimum values in everything, so we make those 1, 2, 3, 4 and 5, these 1, 2, 3, 4 and 5, and then we could have a strip of 1, 2, 3 here, and a strip of 1, 2, 3 here, like this. I don't know if this works from a Sudoku perspective, but this is clearly the minimum value you could put into this ring. That would be 15 plus 15 is 30, plus another 12, which is 42. So you cannot actually make this ring particularly large. We can't go and put a load of 9s in it. It will definitely exceed 45 if we do that. I'm now not sure. Yeah, okay, there isn't much pressure being exerted by the blue ring on the orange ring, though, because the orange ring I was trying to put high digits into, and the blue ring clearly is going to have to take quite low digits. So the two of them together, sort of, they're natural partners. Let me just think about this. Right. Okay, I can improve on that minimum sum, I think. Yeah. So what I did when I just generated that minimum for the blue ring is I put 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5 here, 1, 2, 3 here, and 1, 2, 3 here. In other words, I put 4 3s into the blue ring. I can't put 4 3s in the blue ring because the blue ring only touches 4 different boxes of the Sudoku, and I definitely can't put a 3 in those cells because there's a 3 here ruling it out. So I could put a 3 in those 4 cells, I could put a 3 in those 5 cells, and I could put a 3 in those 4 cells, but I couldn't put 4 3s into the blue ring. So the actual minimum for the blue ring is I could put 4 ones in, I could put 4 twos in, I can put 3 threes in. Now, can I put 4 fours in? No, this is a beautiful puzzle. If this is how you're meant to solve this puzzle, this is absolutely beautiful. You can't put 4 fours in the blue region because if I want to put a 4 into one of those 3 cells, and if there are going to be 4 fours, I need to do that because I'll need to put a 4 in there, a 4 in there, a 4 in here, and a 4 in here. If I put a 4 in here, it has to go in the corner. And once I put it in the corner, I can't put 4s in any of those cells, and I've only got 2 units left to put the other 4s in. I could put a 4 in row 9 and or in column 9, but I can't put 3 4s into that string of digits without repeating a 4 in either a column or a row and or a box. That won't work. So now the minimum value for the blue ring is 4 1s, 4 2s, 3 3s, 3 4s, which is 14 digits. So I need 2 more digits. This is 16 digits. I know that because it must be the same size as the Fistmafell ring, which of course is that one. So I've got 2 more digits to pick. So I could have 2 5s. So, what does all that add up to? 4 1s add up to 4. 4 2s add up to 8, so that's 12. 3 3s add up to 9, so that's 21. 3 4s, so that's 33. And 2 5s is 43. Well, that doesn't seem very different to what I got before. I can't remember what I got before, but it doesn't seem to be much improved. 43, and I've got to get to 45. Oh, bobbins. So it's a 45. Is there some reason I can't put 2 5s into this ring? 5s, 5s, 5s. So 5s. No, I can put 2 5s in. Well, unless that's a 5. Then I could only put 1 5 in. Oh! Well, here's a small point. What are those 5 digits? That is interesting. Those 5 digits cannot be 1, 2, 3, 4 and 5, so must include at least one digit that is not 1, 2, 3, 4 and 5. So there must be at least a 6 in those blue squares, and I haven't catered for that at all in my 43 total. So now the minimum is 4 1s, 4 2s, 3 3s, 3 4s, a 5, and I suppose a 6 in there, and that's 44. So we're now only 1 away, and that means what? I don't know. I think we can. Well, simple ways we could deal with that. We could have 1 7 in there, and then everything else would have to be. We'd have to have the 4 1s, 4 2s, 3 4s, 3 3s, 3 4s, a 5 and a 7. Or we could have. We've got to be a bit careful with this actually. Because we must have 4 1s, we must have 4 2s, and we know that because if we try and get rid of a 2, we've only got 1 degree of freedom, so we'd have to then change that 2 into a 3, which we can't do because I've already assumed 3 3s and I can't have 4 3s. So there must be 4 1s, there must be 4 2s. If I reduce the number of 3s and convert one of the 3s into a 4, that doesn't work because I can't have 4 4s round here, so I can't do that either. So there are exactly there are 4 ones. There are, hang on, let me just do this. There are exactly 4 ones. There are exactly 4 2s. There are exactly 3 3s, and we know that they must go in those squares. Now 4s, if I I know that there could be 3 4s, but if I take one of those 4s out and replace it with a 5, that would be possible, because we can have 2 5s, can't we? I can have 5s here and 5s here, and then have a 6 in there, and that will work. So I can't do the same thing with 4s. But 3 can't go in. 3 can't go in those squares. So 3 is forced into green in both of those strings of digits, along with 1 and 2. Oh, this is gorgeous. Good grief. Yeah, there must be a 1 and 2 in there, and there must be a 1 and 2 in there. So where does the 1 and 2 go in row 4 of the grid? It must go in there, along with a 3. So that's a 1 2 3 triple. And the same is true in the columns. So we've got 1s 2s here, 1s 2s here. Where does 1s 2s go in this column, along with the 3 up there? So that's a 1 2 3 triple. Now, the annoying thing about this is it's not closing the gap, is it, between the green and the orange? So it's still absolutely possible. I can't remember what the minimum was here now. It was 61, wasn't it? So this is still possibly a minimum of 61. If this is a 4, that's a minimum of 61. And that puts not a lot of pressure on this. 4. Well, that 11 cage is getting tricky though now. If that's a 4... No, right. Oh, have I broken the puzzle actually? Hang on a minute, I might have broken the puzzle. No, I haven't broken it. I just don't think... Or have I? Hang on a minute. I don't think this can be a 4. If that's a 4, how do I make 11 work down here? And the reason I think this 11's under pressure is the 1, 2 and 3 in box 8. Only one of those digits could ever appear in the 11 cage. So if 4 is here, these two squares are a minimum of 5 plus 6 equals 11. I can't put 0 in that square, so that does not work. That is not a 4. So that square is a 5, 6, 7, 8 or 9. But the higher it is, the more pressure is getting put on the orange cells. Let me just think about this for a second or two. So now the minimum for green is not 61 anymore, it's 62. $62 here. This cage now has got a 4 in it. Is that what we're saying? I think it is. It must have a 4 in it. Four, 5, 2 or 4, 6, 1. This had a maximum of 66, didn't it? 7, 9 here. 7, 9, 8, 24, 29, 32. That's the maximum value for those squares. So these squares here have to be at least equal to 30. Because this is a minimum value of 62. There's no reason these have to be different, though, is it? Because if they had to be different, they would have to be 6, 7, 8, and 9. Is that in any way constrained? If there is a repeated digit in these dominoes, that repeated digit cannot be a 1, 2, 3. So it's at least a 4. Oh, it can't. Oh, no. It can't be 4, 5 either. They'd have to be a repeated 6. So it actually ends up in this square. That's weird. That's weird. And that removes, actually, that's quite interesting, because that means this cannot be 9898. Because if this was 9898, that becomes a Schrodinger cell. If you try and repeat digits in these two dominoes, look what happens in box. Where does these digits now go in this box? Well, they have to go in those cells in some order. Whoopsie. This has to be in. 2 of these cells now have to be 8 and 9. 2 of these cells have to be 8 and 9. And now where do you put 8 and 9 in this box? Both of them in that cell by Sudoku. That won't work. So you can't now. You can't now have. You definitely can't have 8, 9, 8, 9 here. And any digit you do have ends up in here. I'm wondering whether we can actually use maths here. So let's imagine those two squares repeat. So I don't know what these are. Let's make them 9, just for the sake of an exposition. We now know this square is a 9 by Sudoku, because there will be a 9 here and a 9 in one of those 3. But now, in terms of the sort of bare facts of the puzzle, we know that the green cells equal in total the orange cells. But I know this digit. I can remove one of these yellows and remove this digit. So I'm going to remove 9 from both sides of the equation like this. Let's get rid of those cells. And now I know that these 8 digits here have to add up to these, however many digits that is over there, 15 digits. But I know the value of these 15 digits exactly because I know what these strings are. So I've got 12 plus 45 is 57. So these have to add up to 57. If you have a repeated digit in this domino, and you can't have 2 repeated digits or that becomes a Schrodinger cell. If you have a repeated digit, you've got to be able to make those squares add up to 57 exactly. So is that possible? We know we could make those 7 and 9. So we'd have 32 in those cells. And we've got 3 more cells there that would have. It doesn't work. That is so beautiful. Good grief. That this doesn't work. These cells here, the remainder of the orange box, these 3 cells have to add up to 25. But how can we make those 3 cells add up to 25? You might say, oh, well, you can because you can repeat a digit. You can't repeat a digit because remember, this is a 9. Because I've repeated the digits here. So if I try and repeat another digit, I create a Schrodinger cell. If I can't repeat a digit, the maximum they can be is 7, 8, and 9, which is only 24. It's not 25. It doesn't work. It's impossible. So this is absolutely beautiful. This is absolutely beautiful because now we can come all the way back here. And we've now proved it is not possible for there to be a repeated digit in these 4 cells. And therefore, but we know they have to add up to 30 at least, so they're all different and they're 6, 7, 8 and 9. There we go. And this has to be a 7-9 pair in order to get this whole combination to add up to, I think it was 62, we said. Let me think about that. Is that correct? We've got 29, 32 and 30, 62. Yes, so now we know this digit as well, because we know that these were adding up to 57 plus whatever this digit is, and we now know that must be a 5 to give us the 62 we need. And now we can get rid of 8s from these cells. And this is so peculiar, because now I don't know whether I'm meant to focus on the blue ring or the orange ring. But anyway, I think we can do some Sudoku here. There's got to be a 5 there. There's got to be a 5 here. There's no longer a 5 possible in the 11 cage. Yes, yeah, okay. This is forced. This domino here must be a 4-6 pair. That's the minimum it can be, but it can't be any greater without making this a 0. So 1 comes out. Oh, this is lovely. Right, so 1 comes out of... We know that must be a 1 in this threesome, because I have to put 4 1s in the blue ring. That's got to be a 1. That's got to be a 1 by the same token. 1 comes out of these. There's definitely a 1 left down here. There's now a 1 in my 9 cage, which means there's no 4 in my 9 cage. This is either 1, 2, 6 or 1, 3, 5. Don't know if we can do that. What else can we do here? What else can we do? Why have I got a solitary 2 down here? Oh, that actually is a solitary 2, because of course we know that there must be a 2 in this triple, because we had to put 4 2s in the ring. So there's a 2 there, which means that there's no 2 there, which means there is a 2 there. These squares are not 2 anymore. There's a 2 vertically here. So that's not a 2. There's a 2 horizontally here, so that's not a 2, and that becomes a 2. Good grief. Now, I sort of think that has to be a 4, but I think that's more by... Might not be true. I'm not sure. I just sort of think we have to try and keep this ring down, and obviously this square can't be a 1, 2, 3 or 5. I've got a 3, 5 pair here now. So 4, 6 here. So there's no 6 in these squares, which means there's definitely a 6 in those squares. We can't put a 1 in any of these squares. Oh, I see. These squares are a triple, are they? They're a 2, 3, 5 triple. That's not a 5. So is it the same thing again? Do we need a 4 in that 13 cage, a bit like we needed a 4 in the 11 cage? If there's no 4 in here, there's this, yes, it is. It's exactly the same. That would have to be a 6, 7, and this would have to be a 0. So there is a 4 in here. Yeah, okay, and now Sudoku tells us this square in the middle is a 4, so our sort of conjecture was correct. The 9 cage is not now 1, 3, 5, because there's a 3, 5 here, so this triple is a 1, 2, 6. That which forces a 4 and a 6 by Sudoku. This square here, oh, lovely, look at row 7. By Sudoku, this square is a 3 or a 5, and it sees a 5, so that's a 3. That's a 2. We needed to put a 2 in the box. That's a 5. That's a 3. This square here is a 7, 8, or a 9. Let's try and make sure I scan. So we know what this triple is now. It's the other digits in this box, so it's 1, 4, and 6. Oh, so this did turn out to be 1, 2, 3, 4, and 6. Oh, and we should check. I've got to check. Sorry, I've got to check here. Because I now know, of course, all the digits on this ring, and I think they have to add up to 45. I've got 15 here, 18, 24, 35. These have to add up to 10, and they do. 2, 3, and 5. There we go. So the geometry, the universe is in order. That is what we've just proved. Now these, right, we've got a 4 in here, so the other 2 digits add up to 9. Right, so this is not a 3, because if it's a 3, this has to be 3, 4, 6, and there's a 6 in here already, so that's got to be a 2, and therefore these squares are a 4, 7 pair, and everything is sort of flowing now from being absolutely impossible. The puzzle is actually becoming tractable. Now we can get rid of... Oh, we've got a 3, 9 pair here now, so those can't be 3. In fact, there's a 3 here, so that's a 3, 9 pair by force. We might be able to get this cage now. Oh, especially as there is a 2 in it. So the other 2 squares in here have to add up to 11. And we're not looking at 2, 9 or 3, 8. Or 4, 7 actually, because if we did try and make this 2, 4, 7, it breaks that square. So this is 2, 5, 6. Exactly, which means that square is not a 4. 2, oh, that places the 6 in box 6. I've now got a 7, 9 pair, which fixes the 4 and the 7, which of course bounces back down there and does the same thing. That's got to be an 8 in that square. These squares have got to be a 6 and a 9. Don't know if we know how to do that. 6, 9 here, we know these don't repeat. So this has got to be a 7, that's got to be an 8, that's got to be a 9. These squares have got to be 7 and 8, which bizarrely enough is not fixed. That's a 7 or an 8 by Sudoku. Oh, look at this column. That's a 6 or a 9, it sees 9. That's a 6, that's a 6, that's a 9. These squares have got to be 7, 8 and 9. That's not a 9, that's not a 9, this is a 9. 3 here. No. What have I not done? I can hear the howls of rage from the comments. 6 here, 6 here, 4 here, 4 here. Okay, so now this is a 7. And we've got to put 1 and 8 into those cells, which is probably doable, and I'm not seeing how to do it straight away. Okay, so what about... I've not used that cage. So what are the options for this cage? It's not 2, 9, 5, 6 or 4, 7. It's 3, 8, and we can do it. We can write it straight in. So 8 and 3 go in. Oh, that's nice, actually. It gives me a 7, 8, 7 here. Knocks a 3 out of this square. This has now got to be a 3 by Sudoku. That's a 3 by Sudoku. That's a 3 by Sudoku. These squares are 6, 8, and 9. Which you can probably do, but I can't see how. That's not 8. No. Okay. That's not 9. Okay, what are the... Oh, that's got to be a 4 by Sudoku. So this square here is a 9 to complete row 8, which means that's not a 9, which means that is a 9. Okay, where does 5 go in this column? This 5 means it can't go here, so I think it's got to go into that square, which gives us a 1. Gives us a few other things as well, look. That's now a 6 by Sudoku. This is a 2, this is a 1. This is a 1, this is an 8. That can't be a 5 anymore. So we need 2 and... Oh, bother. 2 and 6 into that square, which seems to be fine. Oh, that square is a 5. Okay, let's have a look at these. 5s and 7. Oh, 5 and 7. I can do that. 5, 7. Yes, and this 7 is nice because it places a 7 exactly there, which gives me the 7 and the 8, which places an 8 and an 8 and a 6, a 2, a 6, a 2, and a something. A 6. Does look like it's correct. Let's click. Yes. Wow. Wow. 50 minutes. Okay, well that didn't feel like... I mean, that's flown by for me. Cloaked in night winds indeed. That, I mean, that's a sensational debut, Barrels. There is so much to admire about this. What I loved about it is it takes something we thought, or I thought I knew and understood, and it makes you think about it in different ways. So, you know, if this puzzle had been set up differently, with the sort of, you know, the Aard thing more brought to the fore, it would have ruined it a bit. We really had to sort of work on it and discover the relationship between, firstly, that this was a 3x3 we were focusing, and this was the 4x4 we were focusing on. But then to bring back our knowledge of Aard and work out that this added up to 45. And that was, I think, pretty crucial, because I then had to work quite hard to work out what sort of things were on this ring. And in turn, that sort of backed into some logic with 1s, 2s and 3s up here. And then the thing that I thought was absolutely beautiful, was realizing that, well, thinking about the sum of these digits possibly being 30, and then thinking about whether they could be a repeated digit, and working out they couldn't be. That was absolutely glorious. I loved that. I mean, sensational setting. Wow. I look forward to your next puzzle, Barrels, with some interest. I hope you enjoyed going through that with me. Let me know how you got on in the comments. I look forward to reading them, especially when they're kind. And I've just remembered I didn't answer the crossword clue, did I? Where is the crossword clue? Come back, crossword clue. All is forgiven. So, bringing up a child causes ... How do we solve this? Well, we have to read it correctly. It's a cryptic definition, which means that we just have to read it and think about it cryptically, and we will realize what the answer is. So if I read it differently, see if you can get it. Bringing up a child causes. Now, bringing up here is a bit... if you bring up your food, that's the way you might want to think about this. If you bring up your food, you vomit. And what sort of vomiting is associated with what might a child cause? Morning sickness. So bringing up a child causes is a reference to morning sickness. It's incredibly well worded. It's so difficult to see how this clue, you know, what this clue's getting at, because when you read it, bringing up a child causes, you want to read it as bringing up a child. You know, it causes, I don't know, sleepless nights or something like that. Whereas actually, you have to think about the bringing up bit of it very differently indeed. It's a brilliant clue, isn't it? Let me know in the comments if you enjoyed that too, and we'll be back soon. And we'll be back later with another edition of Cracking the Cryptic.